Mass spectrometry. As you will see, being a spectrometry dealing with the interactions of electromagnetic radiation, the technology behind this technique is actually quite involved. Essentially, mass spectrometry is used for atomic and molecular mass determination. The operating principles are quite simple. A charge is imposed on a particle. That particle is then accelerated by a magnetic field, by an electric field rather. A magnetic field is introduced, which will bend the particle in one direction or other. And depending on how much the particle is deflected, a mass to charge ratio, m/z, is detected. Most particles ionize to z equals 1, plus or minus 1. There are multiple ways in order to achieve this effect. The one thing they have in common is that masses are separated and measured. The most direct way of doing it is called time of flight. In this case, with all the forces held constant, the magnetic and the electric fields, heavier particles will move slower and take more time to go to the detector. A second method is called the magnetic sector method. In this case, the magnetic field is varied in order to change the trajectory of a particle, so at any given time, at any given field, a particle of a particular m/z ratio reaches the detector. Thirdly, you could also have what is called a quadrupole filter. In this case, similar to the magnetic sector, the electric field is what is varied. Again, changing the trajectory and changing the time to the detector. Particles have to be ionized in order for them to be affected by a magnetic field. This is done by multiple different methods. The first method, called electron ionization, or EI, is what is called a hard ionization method. In this case, high energy electrons are used to impact sample particles. After the collision, electrons are ejected from the sample, and an anionic molecular ion is created. Schematically, M plus an electron at high energy goes to M plus in some excited state, and an extra electron is thrown out to give you 2 electrons. This is affected as follows. First of all, one has to produce high energy electrons. To do this, a filament is electroresistively heated under high vacuum so it doesn't oxidize. Electrons are then emitted from the hot heater, and the sample is introduced into the chamber. This type of ionization has 4 different poles. It is a quadrupole. First of all, the electrons are accelerated to give them energy, and they are generally accelerated at 70 electron volts. In this case, the filament is the negative anode, and what is called the electron trap, to complete the circuit, is the positive cathode. The accelerated electrons, as previously explained, will strip additional electrons from the sample due to the force of their collision. Molecular cations are then formed, And these are accelerated to the detector by 2 more poles. In this case, the detector is held at a negative voltage and is the anode. And there's also a repeller, which is a positive cathode, essentially a shepherd to make sure that all of the cations move in the same direction. Finally, a magnetic field is introduced to make sure that all the cations are not only moving in the same direction, but are moving in a fairly linear manner in a stream. In order to prevent oxidation of the filament and also to prolong the life of the cations, a high vacuum is required, generally by a turbo pump or a diffusion pump at 10 to the minus 6 torr. The force of this is actually quite large, which is why it's called hard ionization. You also form molecular fragments with a positive charge. Generally speaking, these fragments are organic pendant groups that can be easily stripped from a sample. And knowing their weight, as you will see later on, is useful in determining molecular structure. A second way to ionize particles is called chemical ionization, or CI, which is characterized as being a soft ionization. You start with a similar quadrupole arrangement, almost identical, or as a matter of fact, completely identical, to the electron ionization. Two major differences. First of all, this operates at a much higher voltage, approximately 2 to 500 electron volts. Also, what is called a reagent gas is introduced in high excess. Reagent gases are essentially small molecules. Things like methane, ammonia, water, butane are often used. Since they are introduced at a very high excess, they wind up preferentially interacting with the electron stream. Their purpose for being introduced is to form an electronically excited state, R star. After these chemical ions are produced, the sample is then sent into the chamber. Chemical ionization is called soft ionization because energy is transferred from the reagent gas to your sample. In other words, some sample molecule M will collide with an activated reagent gas. In turn, itself will be activated, and the reagent gas changes back to the ground state. This leads to 4 possible interactions and 4 different types of samples being sent to the detector. The first one is called a charge exchange and is the simplest one, where the reagent gas forms a cation, and on collision, the positive charge gets transferred to the sample, creating a sample anion. You can also have protonation, in which case, depending on which reagent gas you have some highly protonated reagent, RH+, and in addition to the positive charge, the proton gets transferred to your sample, which then goes to the detector. Thirdly, you can have hydride extraction. In this case, your activated reagent is brought back to the ground state from R+ by stripping an H- or a hydride ion away from your sample. And you now have a sample that has a positive charge and is missing one proton. Finally, the two species can form an adduct, where R plus and your sample combine to form a new molecule, Rm plus, where the weight of the reagent is added to the weight of the sample. Since this operates under the same principles as electron ionization, you still need a high vacuum. Also, as with many other techniques that you will see, the selection of chemical ionization depends upon the sample. It is very useful if you have an unstable sample where fractionization would lead to a loss of information because the sample molecule remains intact. Additionally, what makes this so desirable and so useful is that by changing the analysis parameters, you can select which type of analyte, charge exchange, hydride extraction, or an adduct, is produced. Again, there are multiple ways to ionize a sample so that they can be affected by the electromagnetic field. A third way is called inductively coupled plasma ionization, or ICP, which is another form of soft ionization. In this method, a sample is dissolved, perhaps in water or any other light solvent, and by means of a pump and a gas flow is nebulized into a fine mist. This mist is introduced into a plasma of inert gas, helium or argon. Okay. The plasma is produced by inductively coupling the gas to a radio frequency generator. Since there are a lot of electrons floating around in the plasma, you generally have multiple variants of M/Z ratios produced. And a quadrupole detector is used to collimate and separate these various M/Zs. An advantage of this is that you need a moderate vacuum, a mechanical pump 10 to the minus 3 torr, very simply to maintain the nebulized sample and keep it in the atomized state for it to reach the detector. Ion-coupled plasma ionization is used extensively with inorganic ions and small, stable organic molecules, essentially for pollution detection. Fourthly, you can have another type of soft ionization technique called secondary ionization, or SI. There are many different ways to do this type of soft ionization, the secondary ionization, but they all have several things in common. First of all, the sample is a solid, or it is dissolved in a non-volatile solvent called a matrix. Some sort of ion source, or an ion gun, accelerates a stream of charged particles at the sample. In this case, you are not only transferring charge, you are also transferring momentum, as sample cations are now ablated off the sample. These secondary ions are accelerated to the detector. Initially, they are propelled by the force of the ion being transferred, and then electromagnetic lenses are used to discriminate and collimate them. This is a very simple method because it is purely geometric, where the angle that the exciting ions enter equal the angle that the activated ions leave the sample and reach the detector. As mentioned, there are many different ways of ionizing, and there are many different types of secondary or soft ionization. You've already seen the common components. Variations on this method include what is known as secondary ion mass spectroscopy. In this case, a very high vacuum, 10 to the minus 6 or lower, is required because the ions are actually used to ablate the surface of a sample. They're used to strip the atoms off the surface. Therefore, the primary ions are accelerated at very high powers between 2,000 and 6,000 electron volts. And as mentioned, the sample surface is abraded away as cations are produced and accelerated towards the detector. More gently, you have what is called electrospray ionization, or ESI. This occurs at ambient pressure. In this case, a solvent is forced through a capillary to turn into an aerosol, and the solvent is ionized, and it is accelerated to the target sample. This is used extensively with macromolecules because what happens is the solvent essentially transfers charge and carries away sample towards the detector. So it does not cause fragmentation. However, as the size of the aerosol particles are different, multiple ionizations are routinely produced. This is not necessarily a bad thing, but since the detector looks for M to Z ratios, different amounts of Z's actually expand the range of mass that the detector can find. Another variation is desorption electrospray ionization, or DESI. Overall, this is very similar to regular electron spray ionization. The ionized aerosol solvent is sprayed on the sample. There's no electromagnetic acceleration. The ionized droplets bounce towards the detector. In this case, it is very gentle, and you have zero fragmentation of your sample. As mentioned, it's non-destructive. It is widely used. It can be used for in situ dynamic studies. It is also used since it operates under ambient pressure for field work in forensics, and is FDA approved for clinical studies. Finally, as we look at how to ionize particles and continue looking at variations of secondary ionization, having overviewed the common components, looked at the more powerful secondary ion mass spectroscopy, your basic electrospray ionization, and DESI, the most modern and latest method for electrospray ionization is called matrix-assisted laser desorption ionization, or MALDI. In this case, your analyte is now encased in a solid. The matrix, the solvent, is a crystallizable material. This can be either achieved with a solvent that has a low freezing point, but more interestingly, for biological studies, the matrix can be any crystallizable biochemical host, anything that could take up a drug, for example, a protein, an enzyme, or a virus. There are extra steps. MALDI is actually a 3-step process. First of all, the sample has to be prepared with a suitable matrix and applied to a metal plate, which is held at some potential. In this case, again, gentle ionization. A laser is pulsed that is used simultaneously to ablate the sample and send it towards the detector, and to heat it so that you have heat-induced ionization. Okay. So the analyte is ionized in the hot stream of material heading towards the detector. Once again, this is soft ionization, is non-destructive. So again, your molecules do not fragment, so it is useful for in situ biomedical studies, forensic work, and is also, again, FDA approved for clinical studies. So there are multiple ways of ionizing a sample. Detection, on the other hand, is fairly straightforward from general physics. It relies on 2 common basic principles. The first, the Lorentz electromagnetic force equation, which says F is equal to Q times E plus VB, where Q is the overall particle charge, which would be the oxidation number Z times the fundamental charge E of 1.602 times 10 to the minus 19th coulombs. E is your applied electric field strength, generally measured in electron volts, where 1 electron volt is a joule per coulomb, so an electron volt is 1.602 times 10 to the minus 19th joules per coulomb. B is your magnetic field strength, measured in Tesla, where magnets have odd units. 1 Tesla is 1 kilogram of force imparted by 1 ampere per second squared circulating in a ring. And V is your velocity, measured in meters per second. Essentially, the Lorentz electromagnetic force equation, as the name implies, can be split into 2. The force is equal to an electric force, F sub E, and a magnetic force, F sub M. The electric force is Q times E, which is the force exerted on a charged particle in an electric field. The magnetic force is Q times the velocity times the field strength B, is the force exerted upon a charged particle in a magnetic field. The Lorentz forces impose or impart motion on a particle. Therefore, the other thing that comes into play is Newton's second law of motion, which says force, no matter where it comes from, is equal to ma, where a is your m is mass, a is acceleration, measured in meters per second squared, or the change in voltage with the change in time. The Lorentz equation and Newton's laws come into play when one is separating the ions. As mentioned previously, multiple separation techniques. The first one is called time of flight, or TOF. With basic electrostatics, for a charged particle in an electric field, you first of all have a potential energy. As you saw from Lorentz, the electric field force is Q times E. Energy is force through a distance. So the electric potential is Q times E dx. In other words, the electric potential is Q times phi, where field strength through a distance is phi, the voltage. That particle will also be accelerated. It has a charge, and it will have a kinetic energy, where the kinetic energy is 1/2 mv squared, or 1/2 m times the second derivative of distance with time. Now, under vacuum, so there are no external forces, and under a constant applied voltage, an equilibrium winds up being achieved, where the potential energy and the kinetic energy are equal, or charge time voltage will be equal to 1/2 the second derivative of distance with time. And here is the basis of time of flight. You can extract time. The amount of time it will take a charged particle to travel a certain distance is that distance divided by twice the voltage to the 1/2 power times m over q to the 1/2 power. This winds up being a constant. For a given length of flight tube, dx, at a given set voltage, dt simply winds up being a constant, m over q to the 1/2. So, again, with the length of the tube and the voltage held constant, ions of differing mass will strike the detector at intervals of m over q to the 1/2. Generally speaking, dynode array detectors are used to absolutely determine Q, therefore allowing M to be extracted. Time of flight is used exclusively with the multiple soft ionization techniques. For one thing, ablation assumes that all the ions will follow a linear flight path and won't be bouncing off the flight tube walls. Also, with soft ionization, secondary ions and fragments are minimal at best, non-existent usually. And therefore, you can basically build an instrument to be as sensitive as you want by simply changing the length of the tube. Alternatively, the sensitivity of time of flight can be increased by adding what is called a magnetic sector. In this case, a variable magnetic field is used to increase the discrimination that the detector has between various M over Z's. A perpendicular electric field is then implied over the magnetic field to basically collimate the sample and to expel any ions that have slightly slower speeds based purely on the time at which they enter the chamber. Time of flight separators are the most sensitive types of separators that one can get, because you can basically, once again, engineer it to any sensitivity you want. So again, as we move to separating ions of different mass before detection, time of flight is the most sensitive. The oldest type of detector was called a magnetic sector detector. In this case, the ionized sample is accelerated by applied electric field. This imparts an electromotive force. Fe, once again, is the charge on the particle times the voltage. And gives a resultant kinetic energy, once again, 1/2 mv squared. A variable magnetic field is then introduced to deflect these charged particles. A magnetic force from Lorenz's law is imparted on the particles as well, where F magnetic is, again, the charge of the particle times its velocity times the strength of the magnetic field. Since the magnetic field is curved, a centrifugal force is also imparted, where F sub c is essentially angular momentum, mv squared, over r, the radius of curvature. If a particle makes it through without striking any walls, that means all forces are in balance. Or your Coulombic forces equal your magnetic forces, equal the electric energy, equal the electromotive force. And solving all of these equalities gives you a fairly straightforward solution. The ratio m over q is equal to the field strength squared times the radius of curvature squared over 2 times the voltage squared. Q is the absolute charge, but again, as you know, that is your oxidation number times the fundamental charge E. So the actual data m over z is equal to E times B squared R squared over 2 times the voltage. Detection occurs mechanically, very simply. A fixed slit blocks the detector. Therefore, only particles at specific radiuses of curvature can pass the slit. So in this method, magnetic field strength is scanned so that particles of specific m over z values will sequentially be able to pass through the slit and reach the detector. This is, again, long explanation, but a fairly straightforward method. The data you get out of mass spec is actually m over z, which is equal to b squared over 2 times the voltage, written another way, times your fundamental charge times the radius of curvature squared. E, the fundamental charge, is a physical constant. B is the variable that you, the user, are controlling as it's scanned. Phi, the voltage, is also held constant. So essentially, at any given point, knowing B, phi, and R is directly related to m over z. Or, taking out all the constants, m over z is directly related to the square of the magnetic field at that point. So with multiple separation techniques, time of flight, magnetic sector, and the newest and most versatile in terms of development, quadrupole mass analysis. In this method, 4 rods, 4 poles, are connected in opposing pairs. They are connected to a DC power supply. However, the voltage between each pair is slightly different because there's resistivity introduced variable on each pair. Also, a complicated circuit, the DC voltage is split to an AC rectifier. This rectifier powers a alternating current radio frequency generator. This alternating current is used to alternate the DC offset voltage between the two pairs of rods at a frequency and the radio frequency. How it works, how M sub Z is separated. Ionized sample is introduced. However, since the voltages are not even, there's a DC bias that will cause all particles to deflect. By introducing the alternating RF field, the direction of the bias and the direction of the deflection continually changes. What you basically have is an oscillating change in bias at the radio frequency. So for any given voltage, only a particle of a correct M sub Z is able to oscillate at the correct frequency to make it through the dipole and hit the detector. So quadrupole analyzers work by scanning the radio frequency at different frequencies to allow different M sub Z's to pass through to the detector. So we've ionized the gas. We've discriminated those ions, and now we have to detect them. All detectors have several common traits. First of all, they actually detect charge. More specifically, they detect the magnitude of the charge, Z, 1, 2, 3, whatever. And they also record the time of impact of that charge. The molar mass, or the M sub Z ratio, is therefore always indirectly determined. Given a set of voltage and magnetic field values at a given time, that will determine which M sub Z's are possible at that time. So by changing the fields, you know what could get through M over Z. By detecting the magnitude of Z, one can therefore find which mass is responsible for the signal. This can be done electromechanically, or these days usually digitally, on a computer. There are again a multitude of options. Your common detectors are 3 in number. You can have what's called a Faraday cup, a continuous dynode electrode multiplier, or a charge-coupled device camera, or a CCD camera. So with our detectors, and the most common ones, you first have what is called a Faraday cup, where Michael Faraday, among all of his work, also determined that a charge impinging on a hollow conductor will not create a hot spot. It will actually evenly distribute it around the outer surface of that conductor. So a Faraday cup is created by, first of all, putting an insulating layer scented into a hollow conductive cup. The ion stream under vacuum is aimed at this insulated layer. The ions are discriminated by using what's called a secondary ion shield at a very high voltage, usually around 300 volts. So once again, that only one M/Z at a time can reach the back of the cup. Also, the entire assembly is insulated electrically. Finally, it is encased in what is known as a Faraday cage. Faraday cages do two important things. First of all, very simply, they're electrically grounded to prevent stray voltages and to isolate the signal. However, by their design, they also prevent the transfer of force by induction, either into or out of the thing that's protected by the cage. So essentially, the Faraday cage gives you the cleanest possible signal. And that signal occurs because since you're under a vacuum, once the ions hit the insulator, there's no place else to go, so they travel along the surface towards the conducting cup. This produces an electric current I, which is the signal. So essentially, the number of particles per second is equal to the current I, where 1 ampere is 1 coulomb second squared, divided by E, the fundamental charge again. So Faraday cups are particle counters. You measure current by literally measuring the number of ions that are flowing. This makes them extremely accurate. Among detectors, and the common ones, in addition to a Faraday cup, you can have what is called a dynode electron multiplier, of which there are two types. You've seen this already. They essentially operate on the same principle as a photomultiplier tube. You have multiple plates set at voltage steps apart. Charged particles hitting those plates causes a release of secondary electrons. Since the sequential voltages are always in highest steps, the number of sequential electrons multiplies as one goes down the steps. Your two types are a discrete dynode electrode multiplier. This has individual plates, individual dinodes, at constant intervals of voltage. This is essentially identical to the photomultiplier tube that you've already seen. More ingenious is something called a continuous dynode electron multiplier. This is made from a glass horn that is coated with a semiconductor. Since you have a semiconductor, in order to have electron movement, you need an extraordinarily high voltage. So this is kept at an overall potential of around 1400 volts. As it's a horn and the radius is decreasing as you go along the length, two things happen. The field strength goes up, and the number of impacts and the number of secondary electrons, the electron density, increases. It's no longer linear. As you get closer to the end, you have more impacts and more secondary electrons. These dynode electron multipliers have extraordinarily high gain. One charged particle hitting will essentially give you a gain of 10 to the 8th, a signal of 800 million electrons. The discrete dynode multipliers have better discrimination. However, the continuous dynode multipliers are much more compact and much more common. So finishing up your possible detectors. You have your common detectors, again, your Faraday cup, your dynode electron multiplier, and third and newest is what is called a charged couple device, or a CCD camera. This is based on semiconductor technology. A charged couple device is a layered structure of metal oxide semiconductors, or MOS, capacitors. The capacitors get larger as you go down, so the top layer has the most capacitors, but they're rather small. Subsequent layers have fewer but larger most capacitors. This layering amplifies signal. The top layer builds charge when it is externally energized. CCD cameras can be used for mass spec. They're also used for visible light photography, many different regions, many different applications. These small top layer capacitors discharge to the lower layers either when the irradiation stops or when they become full. The process continues until all the capacitors discharge, where the final discharge signal is the total of all of the other capacitors in the same stack and is greatly amplified. CCD cameras are versatile. Each pixel is composed of multiple stacks of capacitors and is set at an exact point in space on the device. After passing through a magnetic field, multiple M sub z's in the same sample stream will deflect at various angles. Since the pixels are very small and very precise, each one of these M sub z's will impact a different crystal. As once again, much like a magnetic sector, since the voltage and the magnetic field are known, the angle for any M sub z can be calculated. So therefore, depending on when they hit the detector, you can detect multiple values, multiple ions, multiple M sub z's simultaneously with a CCD camera. So, exhaustively, we've seen how to ionize, how to separate, and how to detect. There's one last thing to make the machine run, and that is separation. By this, I don't mean M over Z. It simply means the sample always enters the system containing some sort of diluent, either a solvent or a carrier gas. The amount of the solvent always greatly exceeds the amount of sample. Therefore, to both protect the machine and to get an accurate result, these diluents must be removed before analysis. There are two possible ways of doing this. For the gas phase, you use what is known as jet separation for use in a gas chromatograph mass spec, or GCMS. In gas chromatography, the solute and the solvent are vaporized by being injected into a heated chamber before they pass into the GC. An inert carrier gas, usually helium, propels this vaporized sample through the separation column. So after separation, both carrier gas and solvent have to be separated from the sample before you can get an accurate mass reading. The solvent is simpler. Very simply, what is called a solvent delay is introduced, meaning you give a minute or two before you turn the mass spec on for the solvent to pass through. The carrier gas, however, requires a more ingenious technique, and the amount of carrier gas is reduced by what is called jet separation. As the sample is going through the GC, it is under a pressure of carrier gas. This high-pressure stream is sent through a series of orifices to restrict the flow. These orifices are sequentially under higher vacuum. Since the carrier gas is first a gas, and generally helium, very light, it will be evacuated preferential to the sample. So that after several orifices and several vacuum treatments, a concentrated sample with almost no solvent and almost no carrier gas is sent to the mass spec. The second separation technique, called particle beam interface, is used with liquid chromatography attached to a mass spec. In liquid chromatography, LC, formerly HPLC, high pressure liquid chromatography, you are dealing with solutes that are either very large or very unstable, either way not suitable for evaporation. In this technique, a peristaltic pump is used to force solvent and solute through a separation column at high pressure. Even though there is no flow gas, the solvent must be removed before the sample reaches the MS. Otherwise, once again, you would lose signal and you could damage the mass spec. So first of all, your liquid effluent from the LC is diluted with a large flow of helium, 1 to 2 liters per minute. This diluted sample stream now enters what's called an expansion chamber. As it enters the chamber through an orifice, the liquid effluent with the helium gas is now transformed into an aerosol. Desolvation largely occurs within this expansion chamber. Because first of all, the chamber is heated, and the solvent usually boils at a lower temperature, and it is also under vacuum. So after the expansion chamber, most of the solvent is gone. The analyte moves to what is called a skimmer, another orifice, where it is slowed down and further desolvation occurs. At this stage, you now have a nearly completely desolvated analyte, and now it goes into an activation chamber where it interacts with chemical ionization to become an excited molecule, where it can be sent to the mass spec for analysis. So at the end of the day, you have a lot of things to think about with mass spectrometry. How do I want to ionize? I have electron ionization, chemical ionization, plasma ionization, various forms of electrospray ionization, DESI, laser-assisted MALDI. How do I want to discriminate between different charges and different masses? I could use time of flight. I could vary the magnetic field. I could vary the electric field in a quadrupole. And what's the best way to detect what comes through? Faraday cups actually count individual ions one by one, while dynode arrays have unmatched gain and sensitivity. But CCD cameras have the most versatility. And to get any of this stuff to work, you have to make sure you have a clean sample. So do I use a jet separator or a particle beam interface in order to remove solvent and carrier gas? The answer is, as you will see, there are multiple different combinations possible, and they all depend upon the application. So, as with any other trade, this all comes down to a matter of choosing the right tool for the right job.